What if I told you that the Philippines released 10,000 giant clams, some weighing over 100 kilograms, into coral reefs that had been completely dead for more than a decade, and 5 years later, those reefs are thriving marine ecosystems? It sounds impossible, right? Well, the Philippines actually did this. And the results are so remarkable that marine biologists are calling it one of the most successful ocean restoration projects ever attempted. Dead coral came back to life. Fish populations exploded, water quality transformed, and it all happened because of giant clams. Creatures most people think of as aquarium decorations, not ecosystem engineers. This is that incredible story. To understand why the Philippines would release giant clams into dead reefs, we need to look at what happened to Philippine coral reefs over the past 50 years. The Philippines sits in the Coral Triangle, the most biodiverse marine region on Earth. These waters host over 500 coral species, 2,000 fish species, and countless other marine organisms. 75% of all known coral species exist in this region. It's the ocean's equivalent of the Amazon rainforest. But by 2010, Philippine coral reefs were dying. Decades of destructive fishing practices, dynamite fishing, cyanide fishing, bottom trawling, had devastated reef structures. Blast fishing alone destroyed an estimated 4 square kilometers of reef annually. The explosions didn't just kill fish, they shattered coral structures that took centuries to build. What remained were rubble fields, dead calcium carbonate skeletons with no living tissue. Pollution compounded the destruction. Coastal development poured sediment into the ocean. Agricultural runoff carried fertilizers that triggered algae blooms. Sewage from expanding cities reduced water quality. Coral reefs need clear, clean water to survive. When water quality deteriorates, coral symbiotic algae, zooxanthellae that provide corals 90% of their nutrition, die off. Without these algae, coral starves and bleaches white, then dies. Climate change delivered the final blow. Ocean warming caused mass bleaching events. In 2010, water temperatures in the Philippines reached 2 degrees C above normal for 3 months. Corals bleached across entire regions. Some recovered when temperatures dropped, but many died. By 2015, surveys showed 70% of Philippine reefs were in poor or fair condition. Only 5% were excellent. The ocean ecosystem was collapsing. The economic consequences were catastrophic. Over 1 million Filipino families depend on fishing for livelihood. As reefs died, fish populations crashed. Fishing yields dropped 60% between 1990 and 2015. Fishermen had to travel farther, stay out longer, and catch less. Poverty intensified in coastal communities. People who'd been fishermen for generations couldn't feed their families. The reef crisis was a humanitarian crisis. Tourism suffered equally. The Philippines attracts millions of tourists for diving and snorkeling. But dead reefs covered in algae aren't attractive. Tourist numbers declined. Dive shops closed. Hotels along reef areas struggled. The economic losses exceeded $100 million annually. The destruction of reefs was destroying the economy dependent on them. The Philippine government tried everything. They established marine protected areas, over 1,500 of them. They banned destructive fishing practices. They prosecuted blast fishermen. They funded coral transplant programs where scientists grew coral fragments and replanted them on damaged reefs. Nothing worked at scale. Transplant programs were expensive, costing $50,000 per hectare, and survival rates were poor. Most transplanted corals died within 2 years. The reefs continued deteriorating. Then in 2016, marine biologist Dr. Agnes Sabater proposed something radical. Instead of trying to replant coral directly, why not reintroduce species that naturally create conditions for coral recovery? She'd been studying giant clams, Tridacna gigas, and related species, and discovered something remarkable. These clams weren't just passive filter feeders. They were ecosystem engineers that transformed water quality and created microhabitats supporting coral growth. Giant clams filter enormous amounts of water, up to 200 liters per day for large individuals. They remove suspended particles, bacteria, and excess nutrients. This filtering purifies water, increasing clarity, exactly what struggling coral needs. Additionally, giant clams host the same symbiotic algae as coral, zooxanthellae. These algae photosynthesize, producing oxygen and organic compounds. When giant clams release waste products, they're essentially fertilizing the water with compounds beneficial to coral. But Dr. Sabater's most controversial claim was this: giant clams could seed coral recovery by releasing zooxanthellae into the water. Coral larvae drifting in ocean currents need to acquire these symbiotic algae to survive. In healthy reefs, zooxanthellae are abundant, but in dead reefs, they're gone. Coral larvae arriving at dead reefs can't find the symbiotic partners they need. They die. Giant clams hosting millions of zooxanthellae cells could provide that missing symbiotic pool. The proposal faced immediate skepticism. Dr. Marco Santos from the University of the Philippines Marine Science Institute wrote, "Giant clams require living coral reef ecosystems to survive. They need the reef structure for protection from predators, the water quality coral creates, and the complex food webs healthy reefs support. Dropping clams onto dead reefs is like planting trees in a parking lot. They'll die because the ecosystem they need doesn't exist." Critics pointed out that giant clams were endangered themselves. Overfishing for their meat, considered a delicacy, and poaching for their shells had decimated populations. Wild giant clams were rare. Using endangered species to restore reefs seemed backwards. Shouldn't conservation focus on protecting remaining wild clams rather than using them in experimental restoration? The economics seemed questionable too. Giant clams are expensive. Hatchery-raised clams suitable for release cost $20–50 each depending on size. But Dr. Sabater was determined. She'd secured funding from international conservation organizations intrigued by the innovative approach. She'd partnered with local hatcheries, producing giant clams for aquaculture to source the animals. And she'd identified test sites, reef areas in Palawan province, that had been declared ecologically dead, with less than 5% living coral cover and minimal fish populations. If restoration failed here, nothing would be lost. These reefs were already gone. Preparation began in 2017. Hatcheries cultivated 10,000 giant clams ranging from 10 to 30 centimeters in length, young but large enough to survive in the wild if conditions were suitable. The clams were quarantined, health screened, and tagged with identification markers. Dive teams surveyed release sites, mapping bottom topography and identifying suitable substrate. Everything had to be ready for release in early 2018, when ocean temperatures and conditions were optimal. The logistics were complex. Giant clams are heavy. Even 20-centimeter individuals weigh several kilograms. Transporting 10,000 clams required boats, specialized containers maintaining water temperature and oxygen levels, and careful handling preventing stress or injury. Then came the underwater work. Divers manually placing each clam on the reef substrate, positioning them in crevices providing protection from strong currents and predators. In March 2018, the release began. Over 2 weeks, dive teams working daily placed 10,000 giant clams across 50 square kilometers of dead reef near Coron Island, Palawan. The clams were distributed in clusters, groups of 10–50 individuals spaced 10–20 meters apart. This clustering mimicked natural giant clam aggregations and increased chances of successful reproduction when clams matured. The moment clams hit the reef bottom, questions arose. Would they attach successfully? Giant clams anchor themselves using byssal threads, protein fibers they secrete. But they needed stable substrate. Dead coral rubble shifts with currents. If clams couldn't attach, currents would roll them, causing stress and potential death. Would water quality be adequate? Dead reefs had poor water clarity and elevated nutrients. Could clams tolerate these degraded conditions? The first week was tense. Monitoring teams checked clams daily. Initial mortality was 12%, higher than hoped, but not catastrophic. Most deaths occurred in clams placed on unstable substrate that couldn't attach properly. Surviving clams showed encouraging signs. They were opening their mantles during daylight, indicating their zooxanthellae were photosynthesizing. They were filtering water. Divers observed sediment clearing around individual clams. They were alive and functioning. By month 3, something unexpected appeared. The rubble substrate around clam clusters was changing color, developing greenish-brown tints. Close examination revealed zooxanthellae cells colonizing surfaces near clams. The clams were releasing these symbiotic algae into surrounding water, exactly as Dr. Sabater predicted. More remarkably, tiny coral polyps, millimeters in size, were settling on rubble near clams. Coral larvae were finding the zooxanthellae they needed and successfully establishing. By year 1, March 2019, the transformation was undeniable. Clam survival rates stabilized at 81%, 8,100 clams thriving on reefs where they supposedly couldn't survive. But more significant were the ecosystem changes. Coral cover in areas with clam clusters had increased from less than 5% to 18%. That's a 260% increase in living coral in just 1 year. For comparison, traditional coral transplant programs typically achieve 5 to 10% increases over 3 years, with high transplant mortality. The coral species recovering were diverse. Acropora, Porites, Montipora, species representing different growth forms and ecological niches. This diversity suggested the recovery wasn't random, it was comprehensive reef regeneration. Even more encouraging, the corals weren't just surviving seedlings, they were growing rapidly. Growth rate measurements showed corals near clam clusters growing 3 times faster than corals in reference areas without clams. Why were corals growing faster near clams? Research revealed multiple mechanisms. The clam's water filtering reduced suspended particles that block sunlight, allowing coral zooxanthellae to photosynthesize more efficiently. The clam's metabolic waste products release nitrogen and phosphorus in forms coral can utilize, essentially fertilizing coral growth. And the clam's massive populations of zooxanthellae created a cloud of these symbiotic algae in the water, making it easy for coral to acquire and maintain healthy symbiont populations. Fish populations showed dramatic increases. Before clam release, fish surveys counted approximately 2,000 individual fish per hectare. By 2019, fish counts exceeded 8,000 per hectare, a 300% increase. The fish weren't just more numerous, they were more diverse. Species that had disappeared from dead reefs were returning. Butterfly fish that feed on coral polyps reappeared. Damselfish that require live coral for territories' established populations. Parrotfish that graze on algae and help maintain reef health returned in numbers not seen in decades. The clams themselves became habitat. Giant clams provide 3-dimensional structure on reefs. Their large shells create crevices and overhangs. Small fish, crustaceans, and invertebrates shelter in these spaces, avoiding predators. Essentially, each clam becomes a mini ecosystem, hosting dozens of species. Camera surveys documented over 40 fish and invertebrate species directly associated with giant clam shells, using them for shelter, feeding grounds, or spawning sites. Unexpectedly, the clams attracted larger marine species. Sea turtles, which feed on sponges, and soft corals began visiting clam restoration areas. Rays that hunt crustaceans hiding in reef crevices appeared. Even reef sharks, apex predators absent from degraded reefs, were occasionally spotted. The restoration was recreating the complex food web characteristic of healthy reefs, from microbes to apex predators. Water quality monitoring revealed dramatic improvements. Before restoration, turbidity in reef areas averaged 8 to 12 NTU, nephelometric turbidity units, cloudy enough to impede coral photosynthesis. After clam establishment, turbidity dropped to 3 to 5 NTU, approaching the clarity of pristine reefs. Nutrient levels, nitrogen, phosphorus, decreased 30 to 40%, reducing the algae blooms that smother coral. The 8,100 surviving clams were collectively filtering approximately 1.6 million liters of seawater daily, equivalent to purifying an Olympic swimming pool every 90 minutes. By 2020, 2 years post-release, coral cover in clam areas reached 35%, now exceeding the Philippine average of 28%. Areas that had been declared ecologically dead now had living coral coverage higher than the national average. This was unprecedented. No restoration project had achieved such rapid, extensive coral recovery. Marine biologists visiting the site couldn't believe what they were seeing: reefs literally coming back from the dead. The success attracted international attention. Research teams from Australia, Japan, and the United States visited to study the restoration. Academic papers analyzed the mechanisms behind the recovery. Conservation conferences featured the project as a revolutionary approach to reef restoration. The Philippines had demonstrated something crucial. You do not need to rebuild reefs piece by piece through expensive transplantation. You can catalyze natural recovery processes by reintroducing keystone species. Economic benefits became apparent. Local fishing communities reported increased catches. Fish that spawn on reefs, groupers, snappers, emperors, were returning. Catches per unit effort increased 60% in areas near clam restoration sites. Fishermen who'd struggled for years suddenly had sustainable livelihoods again. The initial $300,000 investment in clams was generating millions in fishing revenue annually. Tourism rebounded. Dive operators began offering clam restoration tours, showcasing the remarkable recovery. Snorkelers and divers wanted to see the giant clams and the reefs they'd resurrected. Hotels in Coron saw occupancy increases. The restoration became a tourism attraction, generating employment and revenue for local communities. Conservation was creating economic value, not costing it. In 2021, the project expanded. Encouraged by success at Coron, the Philippine government approved releases at 8 additional sites across the archipelago. Another 25,000 giant clams were cultivated and released. The model was scaling up. If it worked at multiple sites, giant clam restoration could become the primary strategy for Philippine reef recovery. The additional releases provided scientific insights. Different sites showed varying success rates depending on local conditions. Sites with stronger currents, flushing away excess nutrients, saw faster coral recovery. Sites with better enforcement against illegal fishing had higher clam survival. Sites closer to intact reef systems recovered faster, likely because coral larvae and fish could colonize from nearby healthy reefs. The research was identifying optimal conditions for clam restoration success. By 2022, 4 years after initial release, the Coron site had transformed into a functioning reef ecosystem. Coral cover reached 52%, officially classified as good condition by international reef monitoring standards. Fish biomass exceeded 2 tons per hectare, triple the pre-restoration amount. The reef was providing ecosystem services worth an estimated $15 million annually: fish production, coastal protection from waves, tourism revenue, and biodiversity maintenance. The giant clams themselves were maturing. The largest individuals now exceeded 40 centimeters, approaching adult size. They were developing the vibrant colors, blues, greens, purples, characteristic of healthy giant clams. More importantly, they were beginning to reproduce. Giant clams are broadcast spawners, releasing eggs and sperm into the water where fertilization occurs. By 2022, spawning events were documented, with larvae settling near parent clams. Natural recruitment was beginning. The population was becoming self-sustaining. Long-term monitoring revealed the reef was still improving. Coral species diversity continued increasing. By 2023, 87 coral species had been documented at the restoration site, up from just 12 species before clam release. This diversity indicates ecosystem maturity and resilience. Diverse reefs better withstand stresses. If one species dies during bleaching, others survive and fill ecological roles. Genetic analysis of recovering coral showed surprising origins. Some coral came from larvae drifting in ocean currents from distant reefs. The clam restoration created conditions allowing these colonizers to establish. But other coral appeared genetically related to remnant populations at the site. Tiny coral fragments that had survived on the dead reef, kept barely alive, and now exploded with growth once conditions improved. The reef wasn't just being recolonized, it was regenerating from survivors. Scientific understanding of how clams facilitate coral recovery grew more sophisticated. Research showed clams alter local water chemistry, not just filtering particles, but also affecting pH, alkalinity, and dissolved oxygen. The clam's zooxanthellae produce oxygen through photosynthesis, creating hyperoxic zones where coral grows better. The clam's calcium carbonate shells slowly dissolve, providing carbonate ions that help coral build their own calcium carbonate skeletons. Essentially, the clams are supplying building materials for coral growth. The relationship between clams and coral appeared mutualistic. Healthy coral reefs provide the clear water and low nutrient conditions giant clams prefer. Giant clams create the water quality conditions coral needs and provide symbiont algae reservoirs. Each supports the other. On dead reefs, neither can establish. It's a negative feedback loop. But once you break that cycle, by introducing clams that can tolerate degraded conditions, positive feedback begins. Clams improve conditions. Coral establishes, improving conditions further. More coral grows, and the system spirals toward recovery. Other species benefited in unexpected ways. Sponges, critical filter feeders, and reef architects colonized the restoration sites. These sponges create additional three-dimensional structure and filtering capacity, further improving water quality. Sea cucumbers, detritivores that clean the reef of dead organic matter, appeared in numbers not recorded in years. The ecosystem was reconstructing its functional groups, each playing roles that collectively maintain reef health. Climate resilience testing came in 2022 when ocean temperatures spiked. A minor bleaching event affected Philippine reefs, but the restored reef showed remarkable resistance. Coral bleaching occurred but was mild. Most coral retained 50–70% of their zooxanthellae, rather than expelling them completely. Recovery was rapid. Within weeks, coral had regained normal coloration. Scientists attributed this resilience to the giant clams maintaining high concentrations of free-living zooxanthellae in the water. Bleached coral could quickly reacquire symbionts from this abundant pool. Economic analysis showed the restoration's financial success was undeniable. The original investment of $300,000 had generated cumulative economic benefits exceeding $80 million over 5 years through fishing revenue, tourism, and coastal protection. Return on investment exceeded 26,000%, among the highest of any conservation project ever measured. The Philippine government recognized this and allocated $10 million for expanded giant clam restoration across the country. Community involvement became crucial to success. Local fishermen participated in clam monitoring, reporting mortalities or problems. Children learned about clams in school environmental programs. Coastal communities established marine sanctuaries around clam release sites, self-enforcing fishing regulations. The restoration became a source of community pride. These were their reefs being brought back to life. International replication began. Indonesia launched a pilot giant clam restoration project in Raja Ampat. Malaysia released 5,000 clams in Semporna reefs. Thailand deployed clams in Andaman sea sites. The model was spreading across the Coral Triangle and beyond. Giant clam restoration was becoming a primary strategy for reef recovery throughout the Indo-Pacific. Academic institutions established long-term research programs at restoration sites. Graduate students studied coral recruitment patterns, fish population dynamics, clam physiology, and water chemistry. The sites became living laboratories, generating scientific insights applicable to reef conservation globally. Over 50 peer-reviewed papers have been published on the restoration, making it one of the most studied reef recovery projects in history. Technology integration improved monitoring. Underwater cameras with AI image recognition automatically counted fish and identified species. Sensors monitored temperature, salinity, turbidity, and nutrients continuously. Satellite imagery tracked reef extent and health indicators. This data allowed adaptive management. If problems appeared, interventions could occur quickly. Technology made the restoration smarter and more effective. Climate change adaptation planning incorporated the restoration's success. Models projecting future reef survival under warming scenarios showed restored reefs with giant clams had 40% higher survival probability than reefs without clams. The clams' water filtering and symbiont provisioning appeared to buffer reefs against temperature stress. This suggested giant clam restoration wasn't just recovery. It was climate adaptation, making reefs more resilient to future warming. The Philippine government established a national giant clam hatchery network. 10 hatcheries now produce 100,000 clams annually for restoration. This created employment, hatchery technicians, divers, monitors, while producing the biological material for continued restoration. The country was building infrastructure for large-scale, sustained reef recovery. Policy changes followed success. The Philippines banned all giant clam harvesting from wild populations, protecting remaining natural clams while allowing hatchery production for restoration. Marine protected area regulations strengthened. Restoration sites received enhanced legal protection. Blast fishing penalties increased. The success of clam restoration gave political momentum to broader reef conservation measures. Educational programs reached millions. Television documentaries showcased the restoration. School curricula included case studies on clam-coral relationships. University programs in marine science expanded. Public awareness of reef conservation surged. Surveys showed 78% of Filipinos now view reef protection as a national priority, up from 43% before the restoration project began. Success had created a conservation constituency. The clam's longevity means this restoration will last generations. Giant clams can live 100+ years. The clams released in 2018 could still be filtering water, supporting coral, and reproducing in 2118. This multi-generational timescale means a single restoration investment provides a century of ecosystem benefits. Few conservation interventions offer such extraordinary long-term value. Future research is exploring additional benefits. Can giant clam reefs provide early warning systems for ocean acidification? Sensitive indicators of changing water chemistry? Can clam larvae be used to seed restoration at distant sites? Broadcast spawning captured and larvae transported? Can selective breeding produce clam strains particularly effective at coral restoration? Super clams, optimized for ecosystem engineering. The science continues evolving. The economic model is being refined for replicability. Analysis identified cost-effective restoration approaches. Optimal clam size for release, 15-20 cm balances cost with survival. Ideal density, 50-100 clams per hectare maximizes impact while minimizing cost. Best substrate, stable rubble with complexity supporting attachment. These guidelines allow other countries to implement restoration efficiently. Private sector involvement is growing. Aquaculture companies producing giant clams for food markets are diversifying into restoration supply. Dive tourism operators invest in clam releases, knowing restored reefs attract customers. Even pharmaceutical companies, interested in coral chemical compounds, fund restoration, preserving their research materials. Conservation is becoming a business model, not just government expense. The Philippines' restoration demonstrates principles applicable beyond reefs. First, natural recovery processes can be catalyzed by reintroducing keystone species. Second, ecosystem engineers, species that modify their environment, can trigger restoration cascades. Third, investing in nature's own recovery mechanisms is more effective than human-engineered solutions. Fourth, successful restoration generates economic returns exceeding investment costs. Fifth, community involvement ensures long-term sustainability. Looking forward, the vision is ambitious. By 2030, the Philippines aims to restore 100 square kilometers of reef using giant clam releases, potentially recovering 10% of the nation's damaged reefs. By 2050, sustained restoration could rebuild Philippine reef systems to 1980s levels before the major decline. This would secure livelihoods for millions, protect coastlines from storm damage, maintain biodiversity, and support tourism, generating billions in revenue. The global potential is enormous. Worldwide, approximately 20% of coral reefs are dead, with another 30% severely degraded. If giant clam restoration can recover even half of degraded reefs, that's improving 150,000 square kilometers of ocean ecosystem. The biodiversity implications are profound, saving thousands of species depending on coral reefs. The human implications are equally significant, supporting hundreds of millions of people whose livelihoods depend on reef health. What can we learn from the Philippines' gamble on 10,000 giant clams? Perhaps that nature's solutions, using organisms evolved to perform ecosystem functions, are more powerful than human engineering. That species we overlook or consider merely decorative may be critical ecosystem engineers. That ecosystems want to recover if we provide the right catalysts, and that conservation investments can generate returns far exceeding costs when done intelligently. Where else could this thinking apply? What other ecosystems need keystone species reintroduction to catalyze recovery? What other species are we underestimating as potential restoration tools? The giant clams of the Philippines challenge us to look beyond traditional conservation approaches. Because sometimes the solution to complex ecological problems isn't complex management. It's giving nature the tools to heal itself. And when we do that, the results can be more extraordinary than any human could engineer.